Okay, welcome. Hello, YouTube. So the reading for today, we're going to go through section 7.7, 8.1, and 8.2. And on Wednesday, the plan is to go through 8.3 and 8 to get to 8.3 and 8.4. Now, and again, technically, problems at 8 is due today, and the outline for problems at 9 is due on Wednesday if you're keeping up, and will be completed. The completed version is due 1 week from today, on Monday, April 20th. But all deadlines are elastic, and so what I'm going to, and especially, I mean, I'm afraid that at least I haven't exactly asked your permission about this, but I extended it to myself, and so I'm way behind on grading the homework, but I will try to catch up pretty soon. And also, and as I do that, I'll sort of start gently asking you, how's it going? Can you catch up on the homework? We do have this exam thingy coming up. So speaking of which, tentatively, exam 2 is scheduled for Wednesday, April 22nd. And the idea is that you'll do it on paper and submit it by Canvas and proctor it. It'll be proctored as best we can by Zoom. And so we'll practice this process in the last 5 minutes of class today. So if it gets to 11:40 and I've forgotten this, please remind me. And again, thank you to today's DJ, Kyle too. All right. So any quick questions before we go on? Before we get back to math. Actually, Matt, if there aren't, I might have a quick question for you guys. So my quick question for you folks is the following, and let me actually blow this up so everybody can see it. Oops, that's not what I wanted to do. This is what I wanted to do. Okay, here we go. So here is a quick question, and this is about I hope you all saw the email I sent out about how we're going to change the weighting of for the semester grade question. So would you rather? The general question is that would you rather have more weight on the homework? So, for example, compare, for example. So the thing I sent out was 25% homework, 20% exam 1, 25% exam 2, and 30% final. Oops. Exam 1, 30% final. Versus, so here's another possibility, 30% homework. Well, here's another possibility, 35% homework, 20% exam 1, 20% exam 2, and 25% final. So I'll give you plenty of time to think about this. Sort of, and you could have a sort of a middle ground, which is sort of halfway between this. I'll sort of give you details about that. So, does anybody want to express their opinion out loud or on the chat right now? Second, yeah. So okay. So of the 3 people who have volunteered to say something so far, 4 votes for the second one. So I think this. I can see where this is going, and the person who actually wrote me about this expressed this opinion already. So I think what I will do is I will send out a survey about this just to make sure this is what everybody actually thinks. And so if if this is what everybody actually thinks, I will sort of lean towards the second, something much more like the second. Because so I mean we're gonna try rehearsing taking exam 2 today, and hopefully it'll be relatively amusing. What do you see what the question is? Oh yeah, and so right. So and Koshal asks, what will be a tentative grade scale for the homework? Usually 2/3 of the points is some sort of B, and yes, yes, above 50. It would be fair to say that usually about 50% is some kind of a C. I mean, who knows? All bets are off because of pandemic. I don't know, but I think that's probably where this will end up. Yes. And actually, even if I have to say, even in a regular semester, a lot of those points, when people have sort of point deficits, so to speak, they're sort of lacking. It's usually because they don't do them. So and especially this semester, if you get it done, Dianu, that's quite an achievement these days. We're all trying to get by, just get by here. Okay, so I will send out. Yes, I will definitely send out this survey later today, and I suspect it'll have the same result that people will prefer option 2, but just to check to make sure in case anybody is feeling shy. Okay, so let's go back to where we were. Okay, I have to ask. Let me ask you 2 questions. One, can you hear my daughter in the background? And 2, if I talk really loud, does that kind of block her out? So yes, you can hear my daughter in the background. Okay, that's okay. Okay, but if I talk really loud, I can sort of block her out. Fantastic. Okay, so let me turn the microphone a little bit away from there. And okay, so last time we found that 2 is a primitive element. Oh, I should remind you what that means of F11. So I think that was the very last thing we did, which means that if you look at F11, the multiplicative part, which is the non-zero elements, we found out that is actually 2 to the 1. Let me start with 2 to the 0, which is 1. 2 to the 1, 2 squared. And if you look at all the powers of 2, mod 11, you eventually hit all the non-zero elements of F11, and so that's what we mean by when we say that 2 is a primitive element of F11. Let's see, and do we have enough room here? Well, maybe not. Okay, so what I want to do is I want to make a table here. Oops. Let me erase here a little bit. Okay, so I want to make a double table here. So this is going to be 2 to the I. So this is 1, which is 2 to the 0. And 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, and 2 to the 9th. And so what I wanted to do is talk about the order of each of those elements. And so there's among the sort of facts about the sort of basic facts about oops, there we go, about orders of elements that we mentioned last time is that the order of, if we happen to know the order of some element alpha, and we want to look at we want to know the order of k alpha raised to the power k, we saw that that's the order. Suppose we have that n is the order of alpha. Otherwise this, if I don't establish this to start off with, it's going to just be too messy. So if n is the order of alpha, and the order of alpha to the k is going to be n over the GCD of n and k. And I think last time we just mentioned this as a fact, but I'll actually sort of show you why this is true. So for example, let me make this is 2 to the 0. That's not a good place. Let me start off with, so here we saw the order of 2 is 10, i.e. 2 to the 10 is 1 in F11, but 2 to the n, 2 to the I, sorry, I guess I should want to say 2 to the I. So let me remind you of the definition of order. The definition of order says that 2 to the I is, to say that the order of 2 is equal to 10 means that 2 to the 10 is 1, but no smaller positive power of 2 for 0 less than I is less than 10. So this means that all the smaller powers are not equal to 1, but 2 to the 10 is equal to 1. So let me talk about sort of what this means here in this case and how you apply this idea, this fact, instead of writing suppose in some indecipherable scrawl, let me wipe that out and say if the order of alpha is n and the order of alpha to k is n over the GCD of n and k. So that fact says that the order of alpha to the 4 is going to be equal to 10 over the GCD of 4 and 10. And now the GCD of 4 and 10, you don't have to use the Euclidean algorithm to figure out that one. It's 2, you know. And so the order, so that fact that we saw before says that the order of alpha to the 4 should be 5. And so sort of why is that true? If you look at, so let's look at the different powers of alpha to the 4. So how do you find the order of an element? Well, one way to do this is just to take the look at the positive powers of that element and see what the first time is that you get 1. So alpha to the 4 to the 1 is alpha to the 4, and that's not equal to 1 because we know. Oh, sorry, not alpha, but 2. My bad. So the order of 2 to the 4. Oops. Is 1. Okay, so 2 to the 4 raised to the 1 is 2 to the 4, which is not equal to 1. 2 to the 4 squared is equal to 2 to the 8th, which is not equal to 1. And these so far, this is because the order of 2 is 10, right? So let's see. So now if we go to 2 to the 4th cubed, now that's equal to 2 to the 12th, but that's equal to 2 squared times 2 to the 10. And we know that 2 to the 10, because we computed last time that the order of 2 is equal to 10. 2 to the 10 is equal to 1 mod 11. And so this is equal to 2 squared times 1 mod 11, which is 2 squared. Okay, so 2 to the 4 cubed is 2 squared. 2 to the 4 to the 4th power is equal to 2 squared times another 2 to the 4, which is 2 to the 6. Still not, oh, this is not equal to 1, and this is still not equal to 1. And then finally, 2 to the 2 to the 4th raised to the 5th power is that 2 to the 6 times another 2 to the 4, which is equal to 2 to the 10th. Yes, which is equal to 1. So the point is, there we go. So 5 is the smallest power of 2 to the 4 that gives you 1 mod 11, which means that the order of 2 to the 4 is 5 in F11. Well, in let me I guess I should just draw the symbol in F11 multiplicative. Okay, so that's a little that's not exactly a proof or even an explanation of this fact that that the order of a power is n divided, the order of, if alpha has order n, and if you want to find the order of alpha to the k, then you get n over the GCD of n and k. Well, that's not really an explanation, or let alone a proof of that fact, but it's sort of at least an example. You can sort of see what happens, that it takes, basically, because the GCD of 4 and 10 is 2, and 10 divided by 2 is 5, it takes 5 times to get back to the identity in this kind of wraparound, in this wraparound sense. Anyway, sorry, that's not. So again, yeah, I don't know. We'll get back to this idea later, but I just want to show you that at least an example of where this 5 comes from. It's sort of, when you start taking these powers of 2 to the 4, of 2 to the 4, with this wraparound factor. What am I meant by wraparound? Oh my goodness, are there still this is like a wraparound, like an old man thing? So what is this? This is what I'm calling the wraparound. Do they still make video games where, like, if you go, let me see if I can do this, where if you go off one side of the screen, you sort of appear back on the other side? Do they still make video games like that? Oh, John V. Yeah, it's like oh gosh, Pac-Man. I think y'all might. I think I just watched Wreck-It Ralph 2 with my daughter, so I know people are vaguely familiar with Pac-Man. So you know how if you, in Pac-Man you go off, Pac-Man goes boop, 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 off one side of the screen and comes back to the other. Boop, 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 boop. So this is sort of like wraparound, but with the exponent mod 10. Anyway, yeah, so what happens? So when you take these powers of 2 to the 4, keeping in mind that 2 to the 10 is equal to 1, then that wraparound idea is sort of what gives you the order of 5 here. Oh yeah, John V asked, why? So let me remind you why is 2 to the 10 equal to 1 mod 11, and so let me remind you of where that came from as well. So or let me actually remind you of the fact that we used to sort of calculate that quickly. Oops. If I can ever make this box expand. Here we go. There we go. So recall a fact about finite fields is that if the finite field has order Q, the multiplicative group, and remember, so F11 times the group of non-zero elements under multiplication has order Q minus 1. Also, and another fact we discussed about finite fields, which we will actually get to later, about that, the order of any element of the multiplicative group must divide minus 1. For F11, Q minus 1 equals 10. So this is a field of order with 11 elements in it. So the multiplicative group has only 10 elements in it. So Q minus 1 is equal to 10, must be equal to 10. So every element of the multiplicative group must have order dividing 10. So either 1, 2, 5, or 10. And then when we actually do the calculation, so oops, I wanted this to be red for some reason. I want it to be red, so now like it's red. We saw last week that 2 to the 1 is not 1, 2 squared is not 1, and this is just by brute calculation, brute force calculation. 2 to the 5 is not 1 mod 11. So that's just a brute force calculation, but that's actually, I mean, it is, however, one that is not too hard for you to do maybe right now. I mean, the only interesting one is this is 32, which is not 1 mod 11. So the order of 2 is not 1, 2, or 5, so it must be 10, and 2 must be primitive. I think this is like the last thing we did last time. So John V, does that make sense? How we got that, or do you have any questions? Yeah, and so so that's still a little bit of brute. There's an even more brute force method. This is one we saw. This is one that we saw back in chapter 3. The sort of old school, the older school brute force method is to calculate 2 to the 1, 2 squared, 2 cubed, all the way up to 2 to the 9th, and see that all are not equal to 1 mod 11. So yeah, the super brute force method that we used initially is just to calculate all of them, and then they're all not equal to 11, but 2 to the 10 is equal to 1 mod 11. The order is 10. All right, so does that so I hear someone very faintly has their mic open, which is okay, but just in case, which I don't really mind. I mean, it'd be nice if people actually want to talk about it. Just so you know, I can hear someone very faintly. Nothing embarrassing is going to come over the transom now. Okay, so John B, does that make sense? Yes. Okay. All right. So sorry. So that's what we did last time. Oh yes. So so anyway, if we now apply, so I'm now going to apply this. Actually, so let me first. Right. Okay. So first of all, this order is always 1. The order of 2 to the 1 is 10. Well, we saw that was 10, and so the order of 2 squared, the GCD of 2 and 10 is 2, and so you divide 10 by that GCD, you get 5. The order of actually, let me do it this way. Sorry. So let me undo that. So let me do this in green first of all. Oh no, actually, let me do this keep doing this in blue. So so if the GCD of 10 and k in this case equals 1, the order of our element is 10. Let me see if I can blow this up. So this is in blue, and so again, so what are the powers here? What are the powers k here? Oops, I should make this 2 to the k. Ah, yes, 2 to the k. Great, 2 to the k here. It's going to be 2 to the k. It's very slow when you draw with a mouse, but it's much more precise. Yeah, so in the blue cases, in these blue cases here, the numbers that are relatively prime to 10, which are 1, 3, 5, 7, and 9. Oh, sorry, 1, 3, 7, and 9. You get the GCD is equal to 1, and so the order is 10. So 2 cubed, the order of 2 cubed is 10. The order of 2 to the 7th seventh is 10, and the order of 2 to the 9th is 10. And for what it's worth, whoever, pretty sure whoever is in the has their left their mic open there's some conversation in Chinese going in the background. Anyway, all right, so that's in the case. Those are all the cases where the GCD of 10 and k is 1, the order of 10. Similarly, put this down here. If let's make this green, lime green. If the GCD of 10 and k is equal to 2, the order is 5. Do this so it's more visible. Okay, so and that happens in the case where with 2 squared, order is 5. Change this to green. 2 to the 4th, we already saw. That order is 5. 2 to the 6th, similarly. Oops. That's order 5. Order 5 and 2 to the 8th. So it's order 5. Yep. And let me just do this. The last one in orange. And in the case where, oh, let's see if you're following along here. So so if the order of 2 is 10, then the order, what's the order of 2 to the 5? Anybody want to try typing that in the chat? So again in the chat. 2. All right, so very quickly somebody answered 2. That's correct. Order is 2. And let me just note here that so now so 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, which is 5. Mod 11. 2 to the 5th is 10. Mod 11. 2 to the 6th happens. I'm just doing this quickly, but is 9. Mod 11. 2 to the 7th is 7. Mod 11. 2 to the 8th is 3. Mod 11. 2 to the 9th is 6. Mod 11. Okay. So now the point is that just as you will have to do the homework, this allows you to compute. Once you have one primitive element, this allows you to compute the orders of every other element expressed as a power of that primitive element, but just by using this formula, without having to sit there and take powers of 9 over and over. So does that make sense? So yeah. Someone's watching a different. So we think that someone else is watching a different live stream of something else. That's okay. Yeah. So who has their mic on? Let me see. Oh, hello. Hi, Jin Chan. I'm going to mic you. I'm going to mute you. There we go. I should have just looked at the little control thingy. Okay. Yes. Yes, thank you, Marcel. I should have muted the chat in the first place, the sort of ambient noise in the first place. Okay, so are there any questions about this exercise, about how to find the order of other elements given one primitive element? Is everybody ready to go on? Type yes if you're ready to go on, or type a question if you had it. Okay, not an overwhelming Okay, so I think you just got to kind of do the homework, and so anyway, if again if it's a little bit tricky to follow along right now, just sort of follow along as best you can right now, and then catch up on the homework, and this will make much more sense. Okay, so let me go ahead and continue. So there was like one yes, let's go on, and a lot of I surrenders. All right, so let me let's see. So there's one more. Yeah, before there's one more thing I want to explain. So yeah, so now I'm just gonna. So I want to talk about the magic polynomial. This one, there's one thing I'm actually going to explain, and then a couple facts that I'm just going to quote. So here's the last fact I'm going to explain. So let F be a field of order Q, then every alpha in F is a root of the polynomial x to the q minus x is equal to x to the q minus x, which is you think of as a polynomial with coefficients in F, and consequently x to the q minus x factors over the field F as the product of all the x minus alphas, which is a remarkable, crazy, weird fact. So when in the case where capital F is F11, which is Z mod 11, this means that if you take the polynomial x to the 10th, actually let me do this the other way around. If you take x, so that's x. So when we have alpha in F, that includes alpha equals 0. If you have x times x minus 1 times x minus 2, all the way. So if for some strange reason you decide to multiply together all the linear polynomials corresponding to all the elements of Z mod 11, including the element 0, if you multiply all that stuff together, you will get x to the 11 minus x with coefficients mod 11. What? That is remarkable. Yeah, so that's what this. So in case you might not be familiar with this product notation here. So this is like a sum. So this kind of imposing looking capital pi is like a sum except for products, and that becomes the stuff on the left here. It's the product of x times x minus 1 times x minus 2 all the way up through x minus 10. And so this corollary of that of the stuff that we've been talking about orders of elements is that if I multiply all these things together, we get x to the 11 minus x. What? I mean, if you're feeling really bored, you could try it, see what happens. I mean, there's just some strange mess over here, but somehow all the terms between x to the 10 and x squared all cancel out and give you something 0 mod 11. Amazing. All right, so and I can't, I try not to do too many proofs in this class. I'm trying to emphasize calculations more, but I think this proof is so well, it's kind of fun, so I can't resist. Anyway, so the point is, before we saw, I think this is a pen thing. So from the facts about orders that we were looking at before, we saw, oops, why is that green? I don't want it to be green. I want it to be blue, but we saw that every element of the multiplicative group, every non-zero element of F has order dividing Q. Say order n, where Q equals ND. So if alpha is an element F, and alpha to the n is going to be equal to alpha to the alpha to the q, sorry, is equal to alpha to the n. times to the n times d equal to alpha raised to the n, all raised to the power of d. And remember, because the order of alpha is n, that means that alpha to the n is 1. So this is 1 to the d, which is equal to 1. I think I better switch to pen now. So alpha to the n equal alpha to the oh shoot, my bad. We saw before that every non-zero element of f has order dividing q minus 1. Sorry. Say order n where q minus 1 is equal to n times d. My bad. This is the classic mistake, is confusing the q and the q minus 1. So this is q alpha to the q minus 1. Is an element. I'll use abbreviation. So that means that alpha to the n let me get out the eraser here. So that means that alpha, no. Oh my gosh, there's no. There we go. Close enough. Oh, come on, buddy. Yeah, whatever. So alpha to the q minus 1 equals 1, which means that alpha to the q minus 1 equals 0 for all alpha not equal to 0 in F. And so I think we need another page here. All right, so alpha is a root of the polynomial x to the q minus 1 equals 0 for all alpha in F not equal to 0. That means that all alpha in F, including alpha equals 0, are roots of x times x to the q minus 1, which is x to the q. That is our magic polynomial, x to the q minus x. So if alpha is a root, if alpha is a root of x to the q minus x, that means that x minus alpha divides x to the q minus x. And remember why this is the factor theorem, which we talked about way, I can't remember. I think we talked about this maybe in chapter 3. I don't remember. Yeah, it must be chapter 3. The factor theorem from high school algebra. But generalized to arbitrary fields. Polynomials over arbitrary fields. Yeah, this is in chapter 3. Okay, yeah, right. So that's what the factor theorem says. If alpha is a root of x to the q minus x, that means that x minus alpha divides x to the q minus x. So it must be the case. So x to the q minus x factors. There's only one possible way for x to the q minus x to factor, it factors as x to the q minus x is equal to the product over all possible alpha in f of x minus alpha, because the degrees, and if you're sort of wondering, if you're feeling a little fussy, this is because we know that if you're feeling a little fussy about this, we just showed that everything on the right hand side must divide everything on the left hand side. Put it this way. So we just showed that the details of this are that we just showed that the right hand side divides the left hand side, but and the degrees match, and the leading coefficient is 1. So the right hand side must actually be equal to the left hand side. Oof, okay. Anyway, so yeah, that's maybe a bit of a digression for given our class, but okay, given sort of the goals of our class, but yeah, so that proves that the magic polynomial is actually the product, x to the q minus x is actually the product of the product of all possible x minus alphas, where alpha regions over all elements of the field. I mean, it's a proof that this actually always works no matter what your finite field is. Amazing. Okay, so any questions about that so far? Any questions about the magic polynomial? Okay, so let's go on to sort of a more descriptive mode. I'm just going to sort of talk about some facts, and then and ask you not to worry about the proofs. Yeah, I'm not sure, and I'm not sure we'll actually apply these facts to make money, so to speak. But it would be remiss of me not to mention them. So let F be a finite field of characteristic P. So remember, every finite field has a sort of a prime P associated with it, that where there's a copy of Fp inside it. So if capital F is a finite field of characteristic P, then F is isomorphic to. Remember what isomorphic meant? We sort of saw that last week. You can sort of construct that field by taking polynomials, Fp bracket x, the polynomials with coefficients mod P, and modding out by some irreducible polynomial m of x. So we're going to look at an example of this in a minute, and what this theorem says is that example is the only way to construct a finite, or that every finite field can be constructed in this manner. You might as well think of it this way. And then the other and the sort of the classification theorem says that if P is a prime and E is a positive integer, there exists at least one field of order P to the E. But conversely, if F and K are both finite fields of order P to the E, then F and K are isomorphic. So in other words, we think of them as algebraically. Remember what isomorphism means. Isomorphism means to say that two rings or two fields are isomorphic means that algebraically we can think of them as being the same. So because any two fields of order P to the E are isomorphic, algebraically you can think of them as being the same. And so if Q is equal to P to the E, where P is a prime and E is an integer greater than or equal to 1, we may therefore define FQ to be the field of order Q. So there is such a thing as the field of order 23 or the field of order 49. I mean, you could try to construct them in different ways, but basically they're all the same because they're all isomorphic. And so this field, the field of order Q, is also sometimes called the Galois field of order Q, or GFQ for short. I think this is a notation that this GF of Q is something. Let me sort of just say why I mentioned this here. So this notation GFQ, what that's about. So we won't use this notation very much at all, but it's common in the outside world, in what they say in the literature. But when other people talk about finite fields, especially in engineering, So when people talk about finite fields in communications and stuff like that, they will usually, instead of saying FQ, usually they'll say like GF of Q, the Galois field of order Q. So just so you know, I do want you to be able to go out and make money with all this stuff after all. So when you see this notation GFQ, that really means that's what we call FQ. Okay, so yeah, there's so again. So all finite fields can be constructed as mod some single polynomial m of x, and so that's what the first theorem says. And the second theorem says that they're sort of summarizing. There exists a unique, so this is the way this is often phrased, there exists a unique finite field of order p to the e. And that if you combine that with the previous theorem, that unique finite field of order p to the e is constructed by taking polynomials with coefficients mod p and killing a single fixed polynomial of degree e. Right. So here's the summary. So again, take it from the top. So here's our 5 facts for finite fields. I'm going to take a risk here and do this full screen. Let's see if this works, so everybody can read it. So the characteristic of a finite field must be some prime p. So in any finite field, there's a prime p associated to it, and the order of that finite field must then be q equals p to the e for some positive integer e. Every finite field has a primitive element, or another. This is often mentioned as the multiplicative group of a finite field must be cyclic, and we'll see what that means when we get to chapter 10. Fact number 3: if capital F is a field of order Q, then every alpha in capital F is a root. This is the magic polynomial thing of x to the Q minus x, or in other words, alpha to the Q is equal to alpha for every alpha in F. In other words, x to the Q minus x factors as a product of all possible linear terms of the form x minus beta, where beta runs over all elements of F, including 0. Fact number 4: every finite field of characteristic P is isomorphic to, or can be constructed by, Fp bracket x mod m of x for some irreducible polynomial m of x. And I guess I should add to this. If the degree of m of x equals e, and the order of the field is equal to p to the e. That kind of follows from stuff that we've mentioned before, but you'll sort of see how that works, and we get to our worked example. And then finally, for any prime p and any prime power q equals p to the e, there exists a unique field, a field fq of order q that is unique up to isomorphism. Whew. So there are the 5 facts about finite fields. So any questions about those 5 facts? This is the big takeaway from section 7.6, what you need to know. So are there any questions about those 5 facts about finite fields? Yes, are there any questions, or are we good to move on? So you can either type a question or say move on in the comments. Okay, and again, if you need to catch up, that's okay. All right, there we go. If you need to catch up, that's okay. This is sort of a good goalpost, sort of a checkpoint benchmark. It's a good benchmark for where you need to be by the end of section 7.6. And I think actually looking at our next example will help. But again, if you're worried about if you're looking at this like, oh my God, what is he talking about? Then the way to sort of achieve this benchmark is to get caught up on homework, as much as I need to get caught up on the homework. So this will always be on YouTube for all semester, and so you can always go back and look at this. Okay, let's go on and look at a concrete example. So as I say, worked examples. All right, so let m of x be x to the fourth plus x cubed plus 1, which is an irreducible polynomial in F2 bracket x. We're going to define F16, like the aircraft, I guess, to be F2 bracket x mod m of x, and we're going to let beta be a root of m of x in F16, or in other words, so the abbreviation for for this big construction, that's saying like, oh, take all the polynomials and we set this polynomial equal to 0, and we use beta to be an abbreviation for the image of x in the quotient ring, is that we say that F16 is F2 bracket beta, where beta is a root of m of x. So so the first thing is that here's a sort of I'm going to count to 10, and then I want you to try to, if you see this, if you know the answer to this, type it into the chat box. The elements of F16 are polynomials in beta of degree at most, and I want you to think about this as I count down from count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so m is a polynomial of degree 4. So the elements of F16 are polynomials in beta of degree at most. Count of 3. 1, 2, 3. Type it in the chat. Okay. All right. So well, one person typed it really quickly, and it's sort of unclear as to whether everybody else is going to get this. There must be some anonymous way to do this. There must be some way to duplicate the shouting out, but maybe we actually did duplicate it. So the point is that the elements of F16 are polynomials in beta of degree at most 3, because the degree of m of x is equal to 4, right? This says that degree of m is 4, and so so remember, when your modulus, you want to think of m as being your modulus. Think of m of x as your modulus. When your modulus has degree 4, then the elements of the corresponding quotient ring are the polynomials are sort of in our new variable of degree at most 3. Right. So I want to take the inverse of a random element of F16. Okay. So there are. So remember, there are. Oh, I should say this too. So let me make a little room over here. So polynomials, you pick a polynomial of degree at most 3. You pick 4 coefficients. Remember that we did this as efficients. So remember we did this as a homework problem that you sort of how do you enumerate the polynomials of degree at most 3? Well, you do by picking the 4 coefficients that corresponding to the cube, square, power 3, power 2, power 1, and power 0. So to pick polynomial of degree at most 3, you pick 4 coefficients, each of which is 0 or 1. There's 2 choices. So that's why there are 2 to the 4th 16 elements of the field. Just as we promised. We promised that this would be an element of a field of order 16, and so yeah, we have a field element of order 16. Okay, so now I want to write down a random element of F16, which means there are going to be. So I'm going to take an element gamma. And I want a sort of random element gamma. We've done this before, but I'm going to do it again. So can maybe somebody who hasn't typed stuff into the chat yet today, pick a subset of 1, 0, 1, 2, 3. So just type a couple of those numbers, 0, 1, 2, 3. 0, 1. Okay. So let gamma be beta plus 1. And so, so to remember, actually, let me do this by typing. So to find the inverse of gamma, we're going we solve the equation. We're going to solve the following thing using Euclidean reduction. Polynomials. Solve the following thing. Let's see. So we want to find. So we already have this this polynomial. So the beta, instead of beta plus 1, we sort of we revert back to kind of x plus 1. And that's where that comes from. So we want to find some f of x. Oops. F of x times x plus 1 plus g of x times m of x is equal to 1. So because then sort of mod the modulus m of x, we're going to get that f of beta times beta plus 1 is equal to 1. Yeah, so right, and I'm going to add like a bunch of pages here. All right, I'm gonna add a page. Need to add a page here. So so what we need to do, so we're going to find the GCD of x plus 1 and m of x in the usual way. What was m of x? It's x to 431. Okay, so luckily this is sort of so we have x to the 4th plus x cubed plus 1. Actually, this isn't so bad. And so remember that we to define the GCD of two polynomials, you do these repeated divisions where at each step the remainder becomes the new divisor, and the old divisor becomes the new thing being divided into. Fortunately, this isn't so bad. This is just x cubed, and that gives you x to the 4th plus x cubed, and that gives you a remainder of 1. So that's your GCD. So that's your GCD. Well, which we knew had to happen, but because we knew that had to happen because x to the 4th plus x cubed plus 1 is irreducible, so there aren't going to be any interesting common factors. But we have to show that the way in which that happens, and so we see that x to the 4th plus x cubed plus 1 is equal to x cubed times x plus 1 plus 1, and so x cubed times x plus 1 plus 1 times x to the 4th plus x cubed plus 1 is equal to 1. Remember plus because we're in characteristic 2. Oops. Because we're working in characteristic 2, because the sort of base field is 2, plus is equal to minus. And so you might object, like, how come I didn't put a minus sign when I put this over to the other side? Well, the reason is because minus is equal to plus, because the base coefficients are all mod 2. So this is x cubed. And looking back at what we wanted to find over here, let's see, this is, let me switch to green. So this is our f of x, and this is our g of x that we were searching for, right? This is our, look back here, we're trying to solve for f of x and g of x over here, and then mod. So going back to what's happening in F16, sorry, I guess I should say in F16, which is really mod m of x. And remember, this thing over here is m of x. We get that beta cubed. So the second term over here goes away, and we get that beta cubed times beta plus 1 is equal to 1. And so beta plus 1. Thank you, Nat, for picking a relatively straightforward one where the calculation is not infinite. Yeah, so beta, the inverse of beta plus 1 is beta cubed. Okay, so we've done that before, but I hope I hope maybe it makes more sense this time, or it makes sense again. So so you remember, so to find inverses, find random elements of inverses of random elements, we do this. So any questions about that? So that's something we've done before, and then we're going to do something new in a minute. Any questions? Okay, so all right, so let me talk about orders of elements. So now I want to integrate this with our facts about finite fields. So oh yeah, and we should have this element orders of elements here. So sort of wrapped in facts number 3, we see that I sort of wrapped into facts number 2 and 3. You know, I mean, I feel like maybe I should add another fact, except then it wouldn't be 5 facts for finite fields, it'd be 6 facts, and the alliteration would be gone. I'll have to think about some way to keep this at 5 facts. Anyway, so every finite field has a primitive element, and in particular, I guess I should probably so recall that we had before. So compared to what we had before, this is the case where q equals 16. This is like q equals 16. So the order of any element, the multiplicative order of any element, the order of any element of the multiplicative group, the non-zero elements, divides 15. So that's one of the facts that we had from before. And so what are the possible orders of elements of the multiplicative group of F16? Well, they all divide 15. So the only possibilities are 1. Actually, let me blow this up so I can maybe not write so huge. They have to be the divisors of 15. So they're 1, 3, 5, and 15. So and so we have this. So we have this question: is beta primitive? So let me remind you about how these reduction rules work. So again, so we're working mod x to the 4th plus x cubed plus 1, which means, and beta is a root of that polynomial, which means that beta to the 4th is equal to beta cubed plus 1, right? So sort of by putting that over on the other side, which also means that beta to the 5th is equal to beta to the 4th plus beta. So we get from the first reduction rule to the second reduction rule by multiplying by beta. And so this beta to the 4th, but we just saw that beta to the 4th is equal to x cubed plus 1. So this is not in turn equal to beta cubed plus beta plus 1. So whenever, remember all elements of F16 can be represented as polynomials of degree at most 3. So all elements of F16 can be represented as polynomials of degree at most 3, and so remember, represent as polynomials of degree at most 3, and that gives us a unique, in particular, that allows us to figure out whether something is equal to 1. So let's do that. So remember, we saw that the only possible orders of an element are 1, 3, 5, and 15. So all we really have to check is that beta to the 1. If beta to the 1 and beta cubed and beta to the 5th are all not equal to 1, then we know that beta has order 15 and so must be primitive. So let's check that. So beta to the 1 equals beta to the 1. That's the equals beta, which is oops, the wrong order, which is not equal to 1 because this is represented as a polynomial of degree less than or equal to 3. Beta cubed, well, is beta cubed, and that's not equal to 1 because that's a polynomial of degree less than or equal to 3. Great. So the only one that takes a little work is beta to the 5th. Let's see if I can write 5. Ah, good. But we just saw that's equal to beta cubed plus beta plus 1. And since that's now represented as a polynomial of degree at most 3, that's not equal to 1. So because just as we did, thank you, John V, for that great question about how do we check that the order of 2 is 10, because beta raised to the power 1 and 3 and 5 are not equal to 1, the order of beta can't be 1, 3, or 5, so it must be 15. So beta is primitive. And in fact, and if you calculate, so if you calculate 1 beta squared all the way going up to beta to the 14th using the reduction rules, get every non-zero, magically you're going to get every non-zero polynomial of degree at most 3 in beta. Cool, huh? I mean, if you keep going, you keep beta to the 6, beta to the 7, 8, 9, 10, 11, 12, 13, 14, you will sort of end up getting some kind of random looking order, every possible polynomial of degree less than or equal to 3 in beta. It's amazing. And it's actually the sort of randomness of what happens here is I think this is like a way that people make, like I said, I think I mentioned this before, this is a way to make a sort of duplicable pseudo-random number generator. All right, and so all right, I think I better finish here because it's 11:39. So can everybody now please log into Canvas and get 2 pieces of paper ready? And I guess we will get to chapter 8 on Wednesday. So all right, so everybody, oh, and it's exam time, so I better stop sharing. Oh my goodness, I ran out of time. That's okay. So let me stop recording.